let's talk about independent and dependent events in reference to probability. So independent events are independent of each other, obviously, if the occurrence of one event does not affect the occurrence of the other. So outcome B does not depend on whether or not outcome A happened. To find the probability of independent events, we multiply the probabilities of each event. And we got into this a little bit in my last video. Now, for example, what's the probability of rolling heads twice, flipping heads twice in a row if you flip a coin? Well, the probability of flipping heads is 1/2 the first time, and it's the same probability and the same chance the next time. If I multiply them together, I see that the probability of getting heads twice in a row is 1 in 4. Okay, so you multiply each of the independent probabilities together. Dependent events happen if one of the events does affect the occurrence of the other. So for example, if I have a red and a blue token in a bag, if I pick out the red one, well, obviously you're going to pick the blue one, right? So before I went, you had a 50-50 chance of getting red or blue. After I pick the red one, well, now you have a 100% chance of picking the blue token from the bag. So those are dependent events. To calculate the likelihood of dependent events, we use conditional probability. Given event A and event B, we say that the probability of event B, given that event A will occur, is the probability of P of B not A. So what does all that mean? P B not A is the probability of B given that A has occurred. So that's what I was just talking about, again, going back to those two tokens examples. So say I had a bag that has a blue token and a red token, and I want to know the probability that you will pick blue given that I've taken A. So we'll call event A that I drew red. And I want to know the probability of B that you will draw blue. Now it's pretty obvious that it's a 100% chance, right? So given that event A has occurred, the probability of B is 100%. We'll practice with this. Just get kind of familiar with this notation. So again, this means the probability of A assuming that, or the probability of B assuming that A has occurred as we want it to. Okay, let's practice. So, given a fair coin, find the probability of tossing heads, tails. Okay, so this is a series of independent events because it doesn't matter what my last toss was. It doesn't affect what my next toss will be. So I have to calculate these events. As I've said, that's independent. I have to calculate the probability of each of these individually. So I'll call event A, the probability of A, just how likely is it that I'll toss heads on my first try? Well, it's a 50-50 chance, right? I can do heads or tails. Assuming it's a fair coin, it's a 50-50 chance. Oops. Let's write that in. So a 1 in 2 chance. It would be the same probability the second time around, right? It doesn't matter what I got last time. I still have a 1 in 2 chance of getting heads. And tails is a 1 in 2 chance as well, right? Heads or tails both have a 50-50 shot. So probability of A of getting heads is 1/2. Probability B getting heads again, 1/2. Probability C getting tails is still 1/2. Now, to find the probability of event A and B and C occurring, I multiply each of their individual probabilities together. That means I take 1/2 times 1/2 times 1/2, which is equal to 1/8. So I have a 1 in 8 chance of tossing heads, then tails. Again, we calculated this by first identifying that we were working with independent events, calculating the probability for each event individually, and then multiplying the 3 probabilities together. Let's do another example. So what is the probability of drawing 2 aces in a row from a fair deck of cards? First of all, is this independent or dependent? Now, this is dependent, and here's why. If I take a card from the deck and don't put it back, I've just changed the odds of what's going to happen next. If I put the card back, fine, but we're saying drawing 2 aces in a row, so meaning I didn't replace the card. So, this is a dependent event, and I'm going to have to use this formula to figure it out. So, I need to know the probability of A, probability of getting an ace the first time. This is the first time. And I need to know the probability of getting an ace given that I've already had one on my first try. So this is my second ace. So assuming that A has happened, what's the probability of getting an ace again? I need to figure both of these out. Okay, let's just look at the first event. If there are 4 aces in a deck and 52 cards in a deck, then I have a 4 in 52 or a 1 in 13 shot of getting an ace the first time. Now, if I've taken 1 ace from the deck, how many are left? Moving on to our second ace here. If I've taken 1 ace, there are 3 aces left, but I must also subtract this from my denominator, right? Because that's just the number of cards in the deck. So by getting rid of 1 card, by getting rid of 1 ace, there's now a 3 in 51 chance, was a significantly smaller chance of getting an ace. So I've found the probability of getting an ace and the probability of getting an ace B the second time, given that A has already happened. Now I need to multiply these probabilities together to find the probability of both happening. So the probability of getting an ace the first time and the probability of getting an ace the second time, given that I did get an ace the first time. I multiply these together. So 1 over 13 times 3 over 51, which is equal to 1 over, if we reduce those, 1 over 221. So there's a 1 in 221 shot of drawing 2 aces in a row from a fair deck of cards. Again, to summarize, I found this by finding the probability of A, just the probability that given a fair deck, I would draw 1 ace the first time. Then I found the probability, assuming A has happened, assuming it's gone the way I wanted, I found the probability of drawing an ace from a deck of cards that only has 3 aces in it. I then multiplied those probabilities together, and that's how I got my 1 in 221 chance. All right, let's practice again. Let's say that we have 2 cubes or 2 die, 1 blue, 1 green. Okay, so this means I've got 2 different ones, right? So if they were the same color, I wouldn't be able to tell the difference, but I've got a blue one and a green one. Find the probability that the blue cube rolls a 3 and that the product is less than 20. So not only do I want a blue 3, I also want to say that 3 times whatever the green one is less than 20. So how do we even attack this? Well, same way. Is this independent or dependent? This is a dependent event. This is a dependent event. So I need to find the probability of A and the probability of B given that A has happened. I'm going to say the probability of A is just the probability that blue is 3, right? So the probability that blue is 3 is a 1 in 6 shot, right? And we can see that pretty easily. There's 6 faces to a die. I want to know what the probability of getting 1 specific face is, so the probability is 1 in 6. Now, what's the probability of a product less than 20? So 3 times something is less than 20. In this case, I think it makes sense to, we want less than 20. Just write out every situation that could happen. So I know that my blue die is going to be 3. So the green one can be a 1, 2, 3, 4, 5, or 6. So I've just written out each of the situations. If I got a 1, a 2, a 3, a 4, a 5, and a 6, what would the product of each be? Now I look at all the ways I look at all the ways that I could get a combination that would give me a product less than 20. So notice if I get a 1, 3 times 1 is 6. If I get a 2, or if I get a 3, any of these would give me a situation where the product of the number on each face is less than 20. So 3 out of 6 possible outcomes is a 1 in 2 chance. So the probability of A is 1/6. The probability of B, given A has occurred, is 1/2. So the probability of both is 1/6 times 1/2, which is 1/12. So 1 in 12 shot that not only will I roll a blue 3, but that the product of the blue face and the green face will be less than 20. All right, let's do another situation like that. So again, I have 2 cubes. I've got a blue one and a green one. What's the probability that the blue cube rolls greater than 5 and the product is greater than 24? So first of all, if I can roll a 1 through 6, what's the only thing that I can roll that's greater than a 5? 6, right? So automatically I know that I have to have a blue 6. So first of all, the probability of getting a blue 6 is just 1 in 6, right? It's just as likely as a blue 3, a blue 2, a blue 1, a blue 4, or a blue 5. So 1 in 6 chance of getting that 6. Okay, now what's the probability? Given that I have a blue 6, that I'll roll a green and whatever the product is greater than 24. So again, I'm just going to lay out every situation. Let's ignore that for a second. So how many times do I come in a situation where my product is greater than 24? 6, 12, 18, these are too small, 24 is too small. So if I roll a green 5 or a green 6, I get a product larger. So 2 out of my 6 outcomes gave me a product larger than 24. So I have a 2 in 6 chance of this happening, which is a 1 in 3 chance. So I know both of my separate probabilities. Now if I want to know the probability of A and B happening, I take the probability of A, 1/6, and I multiply it by the probability of B, given that A has occurred, and I get 1 in 18. So there's a 1 in 18 chance that I will roll a blue 6 and end up with a product greater than 24. Let's do one more practice. So let's say we have a spinner. You know the type that come in like kind of children's games, and they'll have some arrow and the board is separated into like pie slices. So let's say we have 10 different colored sections on this spinner. What's the probability of the spinner landing on blue then purple? So we're assuming that there's only one blue space because they say 10 different, and there's only one purple space. Now, is this independent or dependent? Well, this is independent, right? So if I land on blue, it doesn't make it more or less likely that I will land on purple or any other color the next time. So these are independent events, so we use our independent probability. We need to know the probability of getting a blue and the probability of getting a purple. So if I've got 10 different colors and I want to get one specific color, then my probability is 1 in 10. If I have 10 different colors and I want one specific color, my probability is 1 in 10. It doesn't matter which color I wanted, whether it was blue, purple, yellow, indigo, pink, gray, whatever. Each of them is equally likely, and in fact we probably should have specified that each section is the same size, right? So assuming each section is the same size, then that means getting any color is equally likely. So I know the probability of blue, I know the probability of purple, so if I want to know the probability of event A and event B, I multiply their probabilities together. So 1/10 times 1/10, a 1 in 100 shot that you will get a blue and then a purple when you spin this spinner. So I think these are kind of interesting questions because had I glanced at this, I wouldn't have thought it was that unlikely. A 1 in 100 is pretty unlikely, right? I would have figured it was a lot easier to do something like that. So when you take such a simple situation like this and realize that the odds are smaller than you thought, you can start to kind of expand this on a larger scale, like the probability of winning a lottery or something like that, right? So again, when starting these problems, always first identify whether you have an independent or a dependent event. Ask yourself whether the outcome of the second event depends on what happened the first time. Calculate the probability of the first event, or event A as I usually call it. And then if it's an independent event, calculate the probability of event B and any other events. If it's dependent, you need to calculate the probability for dependent. Calculate the probability of event B given that A has occurred. And your final step is always multiplying each of your separate probabilities together.